In this objective, we're going to look at 8.8 properties of buffers. So the learning objective states that we should be able to explain the relationship between the ability of a buffer to stabilize pH and the reactions that occur when the acid or a base is added to a buffered solution. So there's going to be some situations where you have to decide if something is going to be a buffer or not, if something strong like an acid or a base was added to that buffer system. So this is going to be fairly similar to titration problems. But again, like I said, the goal is the weak acid or base and its conjugate must remain at the end. That is the main goal. Okay, so if there is any strong acid or base left, then this is not a buffer system. If just the salt remains, so the conjugate remains, but not the initial weak acid or initial weak base, this is not a buffer system, because here you need to have both the weak thing and its conjugate remaining. Two things need to remain. One thing I want to note, we are going to be using something called a BCA table. This is going to be using the units moles rather than an ICE table. So BCA stands for before, change, and after. It is very similar to an ICE table, but with an ICE table, we don't know how much was being changed in the C portion. So that's why we put minus X and plus X. But in a BCA table, think of it more of like an organizational table. So you will know how much change there will be because we look for the limiting reactant. So we will use a BCA when species react in a chemical reaction. So if there's going to be a chemical reaction, we have particles reacting, we need to put a BCA table. Okay. And then lastly, we have to determine what is weak and strong and what's an acid and base. All of this section right here has to go back to 8.1 and also Unit 4 when we first originally talked about this. So let's look at example 1. We have 50 milliliters of 0.2 molar NH3 is mixed with 50 milliliters of 0.1 molar HCl. Is the resulting solution a buffer? So first things first, let's do on this equation right here. Let's first decide what is weak, what is strong, and what's an acid and a base. So here, I wrote the reaction for us, but you're not always going to get that. Just please keep that in mind. The fact that it was mixed, the NH3 and HCl, that is why they're on the reactant side. So here, NH3 is going to be a base, and it's going to be a weak base. WB is what I'll put for that. HCl is actually one of the 6 strong acids. So I'm going to put SA for strong acid, which means that this product has to be the weak conjugate acid of the weak base. Now, this is an acid-base reaction, because remember, an acid-base reaction will make an aqueous salt, which is that ammonium chloride, and water. Now, we are going to need to get familiar with doing net ionic equations. So back in 4.2, when we talked about net ionic equations, weak electrolytes stay together. Okay. Now, this is going to be, now when I say weak electrolytes, this is going to be a weak acid and a weak base. Okay. Now here, the NH3 will stay together. Next, HCl is a strong acid, so it will break up. Now, I'm not going to write it off to the side, but remember, HCl releases hydroniums, H3O positive, not just H positive. Here we have H3O positive. Now, I don't want to confuse us too much, but here, NH4Cl will break up, and that's because it is an ionic compound, and we really need that ammonium piece. The chloride will be taken off, okay? Here, NH4 positive plus water because it's a liquid. We'll keep it together. Now, you will notice I did not include the Cl minus, and that was my bad, but here they're going to end up crossing off just because of the Cl right here and the Cl right here, they'll cross off in a net ionic equation. So I kind of skipped the complete ionic step. Now, I'm going to teach us how to use a BCA table. So before, change, after. Remember, I said a BCA table is a moles table. So right now, I was told everything about the ammonia, and I was told everything about the HCl, which is the hydronium. You have to remember that we learned about molarity in Unit 3, which molarity is moles over volume. So separately, I'm going to solve for the moles of ammonia and moles of the hydrochloric acid. So ammonia, I have 0.2 molar, N on top, and 0.050 liters, because convert 50 milliliters to liters, it's 0.050 liters. Here I get moles as 0.01 moles of ammonia. Then for the HCl, which I'll just write hydronium, 0.1 molar, and on top, it is still 50 milliliters. I get 0.005 moles. Oops, sorry. Got a little ahead of myself. Here, H3O positive. So let's plug those two values into our BCA table. So right now, I am told the initial starting moles for those two reactants. Now, we will have no ammonium to start with because it didn't say anything about it being produced, okay? Now, how you work a BCA table is you find whichever one is the smallest. Okay, now what's nice with AP Chem, they are going to only be working with 1-to-1 to 1-to-1 balanced chemical reactions when it comes to acids and bases in this Unit 8. So you won't have to worry about, multiplying by 2 or multiplying by 3, whatever. So here you just have to choose whichever value is the smallest. So here, how this works is since the change is not like the ice table change and we don't know how much was consumed, here we just subtract the smallest one, okay? Because what this tells us is this is the limiting reactant. It is the smallest value, so all of it will be used up. So then what's going to happen is all my reactants, the other ammonia, will get the minus 0.005, but our product now will get positive 0.005 because that is a product and also the ratio is still 1-to-1. So here, left over, I have 0.005 of the ammonia and 0.005 of the ammonium. So right now, I have the ammonia and ammonium remaining. So here is the resulting solution, a buffer. You would say, yes, this is a buffer because both components of NH3 and NH4 positive remain. And that would answer the question, okay? All right, moving on, I have example 2. Let's try this one together. Okay, so here let's follow the same steps how we approach the other one. So I'm going to zoom in. Here, HC2H3O2 is going to be a weak acid. This is acetic acid. Also, you can tell that this is the acid because the H is in front. Next, NaOH, sodium hydroxide, is a strong base. So here, that is going to make the conjugate base over here of the weak acid. Now to write my net ionic equation, my weak acid will stay together. What will end up happening is the sodium and the hydroxide will split up, and then that sodium acetate, the product, will also split up, which makes the sodiums cross off. So here I'll have hydroxide, then I'll have the acetate ion plus water. And then I can start filling out my BCA table. So I was told my weak acid and my strong base. So let's solve for the moles of both. So here, let's first start with the acid. So let me erase that. HC2H3O2, here 0.20 molar, and on top 0.050 liters. I get moles as 0.01. And then I'm sure you can probably figure out it'll be the same value, but let's just do it. You'll end up getting, like I said, the same thing, 0.01 moles of hydroxide. So let's plug that into our BCA table. So right now, they are the same value. So here that tells me that they're both going to be limiting reactants, which means I'll make 0.01 moles of the acetate. So all that remains after the reaction ends is the sodium acetate, or should I just say acetate ion? So here I would say, no, this is not a buffer. And that's because only the conjugate base, the acetate, remains. We would have needed the acetic acid to remain with that acetate to be considered a buffer. All right, so before you try this out on your own, I'm going to actually help us first tackle how to write the net ionic equation for this reaction, just because it can be a little different than the ones that we were working with. So let's first identify what's an acid and a base and what's weak and strong. So when you look at the first thing listed, NaHCO3, you may not be entirely sure what it is right this second. So you can always look at the other reactant listed. So the NaOH tells me that this is a strong base. So that means if we're talking about an acid-base reaction, the NaHCO3 has to be a weak acid to make that acid-base reaction occur, which we know a weak acid will be making a conjugate base. We can identify that the Na2CO3 is our conjugate base. Now to write the net ionic equation, we're going to have to get rid of all the sodiums, okay? Now let me first write out what that's going to look like, and then I'll explain why we're going to break those up. So I did tell you when it comes to a weak acid or a weak base, we will not break them up. But when I stated that, I mostly was stating it in the sense of the hydrogen aspect, okay? I'm not saying to break up the H off of the HCO3 minus. I'm talking about that sodium. That sodium is part of an ionic compound, sodium bicarbonate, HCO3. Here, that sodium can be broken off and be crossed off with the other sodium from the sodium hydroxide, with also the product side, those two sodium ions attached to the carbonate. So here, this would be a situation that this would be okay to do so, but overall, this would be our net ionic equation. So I'm going to zoom out. I want you to pause the video and try this out yourself. Find the moles of each, plug it into the BCA table, see what remains. So in this example, this would not have been a buffer because the strong base remains. So I first solved for the moles of each. I got HCO3 minus as 0.01, and I got the OH minus as 0.025. So plugging those into the BCA table, unfortunately, the HCO3 minus, that weak acid, is going to be our limiting reactant. So the NaOH is going to be remaining as 0.015 moles, and then we did make some carbonate, that conjugate base, as 0.01. So even though we did have two things remain, this is not going to be a buffer because the strong base was part of the buffer, making it not a buffer anymore. So here, if you ever see anything strong remaining, it is not a buffer, okay? All right, there's a few other things that I want to talk about, and then this video will be over. So how does a buffer work? And this is going to be assuming we have a buffer in place already. So unlike the previous problems, we were just taking two reactants and reacting them to make products. Here, let's say that we have both buffer components, meaning we'd have, in this case, the HCO3 minus and CO3 minus as both moles in the solution. So this would be like we'd have a value right here, not just 0, okay? A buffer will react with or absorb hydroniums or hydroxides from the strong acid or base that is being added. And this is going to change them into its weak conjugate acid or weak conjugate base, thus avoiding the large pH change. So if a buffer system is composed of, let's say, ammonia and ammonium, and let's say they're in equal moles, so let's say they're both 1 molar, okay? The reaction with a strong acid, if you can change this to H3O positive, this is going to react with what part of the buffer? So here, if you add a strong acid, you have to think acid-base reactions will make water and a soluble salt. So if you add a strong acid, we need the basic component of the buffer. So here, the ammonia, the weak base, will react with that strong acid, which will make the other component of the buffer, the ammonium. And so here, let's say the same reaction occurs, but this time with a strong base, hydroxide. The strong base will react with the acidic part of the buffer to make an acid-base reaction occur. And that will make its conjugate weak base ammonia. So you'll never see an acid-acid reaction or a base-base reaction because that's not going to be a reaction. There's no chemical reaction that will occur if you took HCl and let's say HF together. They're not going to react. You're just going to keep dropping the pH lower and lower. So here, if you're going to make an acid-base reaction occur, it needs to be acid and base, not acid-acid or base-base. Now, last thing, I do want you to notice that the H3O positive, and again, this is just to put it into words, reacted with the more basic part of buffer, while the hydroxide reacted with the more acidic part of the buffer. Again, just putting that down in words. And again, in both reactions, one part of the buffer system was changed into its other part, okay?